last class we were discussing about the field due to a continuous charge distribution, that was a line. Okay. This is from your previous class, that is we had a line of length 2L and we were trying to find out its field, its electric field at a point Z about the center of its of that line. Okay. That is what we were doing, and we finally reached a particular integral. Okay. What does this integral means? This, how do we get it? Let us see. That is, we had considered a small dq here and another dq here, and due to this two small charges we found electric field due to this dq and this dq, and we summed it up, and then what that sum is here, this is, and without that integral symbol we can read it as okay. So, without that integral symbol, this is that electric field, that is due to this dq and dq, and to find the total electric field due to the entire length of the line, we have to integrate this expression, that is this integral. Okay. That is from 0 to L, we integrate only from 0 to L. Why? The minus L to 0, this portion is already contained within this equation, that is why we considered two dq's simultaneously. So, we have to only integrate it from 0 to L. So, from 0 to L. So, that is the next part. Oh, we have to integrate it out. So, let us see how to do that. So, to integrate it, we are doing some substitution here. Here we have a triangle, you can see a triangle here, and in this triangle let this angle be theta. Okay. That angle is theta, and let me write tan theta from that triangle. Now, this is a right angle triangle because it is perpendicularly above. So, that is 90 degree, this is the opposite side, this is the adjacent side. So, tan theta is equal to opposite side, that is x, divided by adjacent side, that is x by z, or x is equal to z tan theta. So, we use this substitution to integrate this expression. So, instead of dx we have to put a substitution, instead of x we can substitute this. So, then dx is equal to, now we know that z is a constant, that means it is a fixed distance, that distance to our field point, that is fixed. So, z is a constant. So, dx is equal to z times tan theta, the derivative of tan theta is sec square theta d theta. Okay. Now, just substitute this x here for this x and dx here for this dx, then we can simplify this integral. So, let us do it. So, this is our substitution. Okay. Now, let us substitute these values, that is this x value and dx value back into this equation, then we get 1 by 4 pi epsilon 0 integral 0 to L. Now, we can take some constants outside, one of the constant is 2, then other constant is z. Okay. So, we can take 2 and z outside. Then what about this lambda? Is lambda is a constant? Yes, in this case, particular case, the lambda is a constant, but it need not be always, it may be a variable sometimes, that is sometimes the lambda may be given as a function of the geometrical variable some x square, or lambda is equal to some x cube minus x or something, anything, anyway as a function of x. Then if it is given as something like this, then you have to put it inside the integral, that means it has to be integrated. Otherwise, if it is a constant, that means lambda is a constant, we can take it outside. So, in this case the lambda is a constant, so we are taking it outside. So, lambda is taken outside, then what is the remaining thing, that is 0 to L dx, the direction is also a constant. So, we can later we can take it outside. So, dx divided by z square plus x square the whole raised to 3 by 2 into z cap. Now, let us substitute the values, which is equal to 2 lambda z I am taking that z cap also divided by 4 pi epsilon 0 into integral. Instead of dx, I can substitute z sec square theta, and there is a d theta also here, So, d theta divided by z square is z square itself into, instead of x, I can substitute x is equal to z tan theta, that is x square is equal to z square tan square theta. So, plus z square tan square theta the whole raised to 3 by 2. Okay. Now we can take an z square outside. So, this is equal to 2 lambda z into z cap. Okay. Okay. Is equal to 2 lambda z cap divided by 4 pi epsilon 0 into integral z c square theta, z sec square theta d theta divided by, let me take this z square outside. So, when the z square came outside, this becomes z square the whole raised to 3 by 2. So, that 2 and 2 get cancelled, then an z cube comes outside. So, an z cube comes outside, then what is the remaining? Let us see. Z square is came outside, that means there is a 1 plus this become tan square theta. So, this becomes 1 plus tan square theta. So, this is equal to, again this is equal to 2 lambda z cap divided by 4 pi epsilon 0 integral. Here we have an is integral z and z cube, we can cancel this z cube later. Now, 1 plus tan square theta is again c square theta, here we have a whole raised to 3 by 2, that is this term itself, that 1 plus tan square theta, the term in the bracket wholly becomes c square theta, the whole raised to 3 by 2 becomes c cube theta. So, sec square theta d theta divided by sec cube theta. Okay. Now, we can cancel whatever is there, we can calculate, we can cancel this sec square theta with this sec cube theta, there remains only a sec theta. Now, here is an z, there is an z, we can cancel it with z cube. Now, what is remaining? 2 lambda by 4 pi epsilon 0, this z can be taken outside, into z cap into integral. What is the integral? D theta divided by sec theta. What is 1 by sec theta? That is cos theta. So, that is cos theta d theta. Now, we can integrate it. So, it is very simple. Now, it is very easy to integrate cos theta, the integral is sin theta. So, this is equal to 2 lambda by 4 pi epsilon 0 z into z cap into sin theta. Now, sin theta has a certain limit. Now, we integrated it. Now, we have to substitute the limit. We are not substituting the limit in terms of theta, but we can resubstitute for theta from the earlier figure. The figure was something like this, that is we had some minus L to plus L, that means the total length of 2L, this was the origin and this was our Z, and we considered a dx here. Okay. From the dx we drawn a line like this, and this is the point where the field has to be calculated. Now, this angle was theta and this distance was x. So, from this triangle earlier we wrote the tan theta which is equal to x by z. Now, from this same triangle we can write sin theta also. So, sin theta is equal to opposite side, that is x divided by what is x divided by the hypotenuse. What is the hypotenuse of this right angle triangle? Yes, we know that one of the side is x, other side is z, that is base and height are x and z respectively. Then its hypotenuse is equal to root of x square plus z square from the Pythagoras theorem. So, we can put that there, that is root of x square plus z square. So, this can be substituted instead of this sin theta. So, let me take it. Okay. Okay. Now, this is equal to 2 lambda divided by 4 pi epsilon 0 z cap into sin theta. What is sin theta? Sin theta is x divided by root of x square plus z square. Now, we can resubstitute the limits, that is from 0 to L. Let us substitute it back. So, let us substitute it back. We get is equal to 2 lambda by 4 pi epsilon 0 z into z cap into. Now, let us give the upper limit. When we give the upper limit, this becomes L divided by root of L square plus z square. That means, here the integral is over x. So, we have to substitute the limit for x itself. So, L divided by root of L square plus z square, okay, that is the upper limit, minus the lower limit. What is the lower limit? The lower limit is 0. When we put that to the numerator instead of x, that wholly becomes 0. So, minus 0. So, this is the answer. Now, we got some weird expression, that is something like this. So, this is equal to, we can calculate 1 2, that is, and here that is it. There is no further simplification. 2 pi epsilon 0 z into L by root of L square plus z square into z cap. This is the expression for the electric field due to a very simple line. So, why I told it is a very simple line? When the distribution becomes more complex, actually the calculation becomes more tedious. Why? Actually, up to that integral it were very easy, that is just a simple integral. In as an expression it was a very simple integral, but we took most of the time in constructing the final answer for integrating it out. So, that is the problem with that equation. That is why we have to further proceed with electrostatics. You cannot use that equation simply to find all the things. So, we need some more mathematical tools and tricks to avoid these integrals from this equation. Even for a simple line charge, we have to do this much of integral. Now, when the systems becomes complex, you have to do you have to spend more time in integrating rather than the physics of electrostatics. So, we find some additional tools and we will discuss about shortly. In the last problem, we have seen that we spent a lot of time in doing that integral. Now, we are going to deal or we are going to find some more tools to avoid that integration, that complex integrations, and some more other tools. For as a preliminary thing, we are discussing a new thing, how we can physically or how we can visualize the electric field, and that visualization of electric field is called electric field lines. Okay. Now, what is an electric field line? Okay. Before going into that, or we can do something else. So, imagine that we have a charge q here, okay, and let at a distance r from this charge, we know the expression for the electric field. It is a point charge, and let here we have a point r, okay, that is a point p at a distance r from this q. We know the expression for the electric field, that is equal to E is equal to 1 by 4 pi epsilon 0 q divided by r square into r cap. That means, if the charge is positive, then its direction will be radially outward. That already we have learnt in some previous classes. Okay. Now, this is the point P and we have r is the distance. Now, we are drawing something, that is we are drawing some vectors. What vectors? We are going to calculate, or we are drawing some representative vectors to address this electric field? How? So, we know that we can consider a point here. So, at this point, what is the value of this electric field? We know that its value is 1 by 4 pi epsilon 0 q by r square into r here, and that is a vector. Let me draw that vector, not exactly with that same magnitude, but representatively at some length this much. Okay. Now, its length is this much. Now, I am going to draw one more, okay, one more at here, okay, at this point. Now, at this point what happened? Now, this vector is for this point, that means the distance is this much, okay. This is our r, that means the magnitude is much higher than that at this point. What happened when we are receding away from that q? When we are moving away from q, the r is increasing. So, since r is at in the denominator, it has to fall. The magnitude of the electric field will fall as you move farther and farther and further. So, so now we draw a nearer electric field as this much length, then a farther electric field vector must be a shorter one. Why? The magnitude is decreasing as you move farther from the charge. So, I have to draw something like this, which is much shorter than this. Then what would be the next vector? That should be more short. So, this is what happens. What this shows is that the intensity or the magnitude of the electric field is getting smaller as you go away from. Okay. Now, let me erase this. We need only the figure. Okay. Now, let us draw it in the opposite direction. Here also we can draw for a nearer point, it is a longer line, then it gets shorter and shorter. So, we can draw something to here, something to here, and one more there, and here also we can draw something like this. No, the next one must be shorter. Okay. Let me remove the heading. Okay, this will be something something shorter than this, then shorter than this. I can draw something to here, here, here. So, you have to only point that the important thing that you have to consider is that its length should be shortened, and if it is a positive charge, its direction should be radially outwards. Okay. So, this is it. So, this is a kind of representation for an electric field. Now, you have to again think that this is not just on a plane, this is a three-dimensional thing, that you have the field lines to here, to here, to here, and also into the board. So, all together it constitutes something called the field lines, and its length shows the strength of the electric field, and the direction of the arrow shows the direction of the electric field. So, but this is not a nicer way, we can change it. I am connecting all this together to make some single lines and trying to draw. Okay, let us see that. So, this is our present field lines. Now, let me draw something like this, that is, you have a Q here. Now, instead of this piece lines, I am connecting it together, something like this. Let me connect it something like this, a single line with an arrow in the same direction. So, here now if I draw the same for here, so the lines will be something like this, something like this, something like this, like this, like this. Okay, this is it. Now, what happened? There is no length element. That means how could you say that as the distance, as you move away from the charge, the intensity is decreasing or the magnitude is decreasing? How will you get that data from here? Because here you have only a single line, but here you had many lines, and based on the length, the decrease in the line segments, decrease in the length of the line segment, you can address the strength of the electric field. But here, how will you do that? Here there is a technique. You just look for the number of field lines passing through a certain area. So, imagine that I am taking a piece, this much of a piece of paper, and let me move it to here. Now I am coming too much closer to here. Now through the same rectangle 1, 2, 3 lines are passing. That means through the same area 3 lines are passing. Now I am moving away from that, too much away. Now only a single line is passing through that. That means when 3 lines are passing through the same area, at that area the intensity is maximum or higher than this point where only 1 line pass through that area. That is how we are keeping the data about the intensity. So we have something called field lines passing through unit area, and we call it as flux, and using that we can measure or we can address the strength of the electric field. And the electric field lines always starts for positive charge, it originates from positive charge, it terminates at negative charge. So for a negative charge it terminate at negative charges, and some other properties are also there. Electric field lines shows, suppose if you have an electric field line like this here, then a tangent at a point will give you the direction, and if so at this point what is the direction of the electric field, at that point draw a tangent to that. And there is very important thing about electric field lines, that is they cannot cross each other. That means two field lines, you never see such a figure, that is one field lines is moving like this and another field lines is coming, that is they are crossing at a point. They cannot cross at a point, because if it cross at this point the field has two direction, one is towards here and towards here, which is impossible. Electric field can only have a single direction at a single point, that is why this is impossible. So the strength of the here, the important thing is that the direction is got from the arrow and the strength is got from the flux. We will deal more about flux in the next class, and also the Gauss's law, that is an outcome of this flux. And thank you.